Hello, and welcome to today's session. As always, I'm your host, Kevin Grote, Staff Systems Engineer here at VMware. Today, we're joined by a colleague of mine, Mr. Paul Irwin. Paul is an NSX specialist as well as a senior engineer and a technical partner manager here at VMware. This is one of his areas of specialization, and Paul does an absolutely fantastic job talking about it. Recently, I asked Paul to walk through a whiteboard on NSX, but a very specific whiteboard. I asked him to talk about what happens in a double-click type environment where we're looking at NSX not just from the basics of what it can do, but also how it expands into multiple data centers, how it helps us eliminate or mitigate the need for VLANs and also physical networking segments, and how it expands our capability from a services and policy perspective as we grow. Now, inside of this, Paul created a session, and I've split it up into a couple different segments for us. The first one walks us through the core understanding and what we can do when we start to think about extensibility. And then in the second segment, we're going to be looking at how layer 2 extensibility factors into this and how we start working in ideas like procedures, policies, and other services integrations into the NSX space. I'm really excited to bring this to you, and I know you're going to absolutely love these two sessions. So without any further, let's go ahead and join Paul as he walks us through this whiteboard on NSX.
And NSX happens to be one of my specialities at VMware. So I wanted to make sure that, we kind of covered a broad spectrum of capabilities. And, today's session assumes a couple of things. Number one, that, you're familiar with NSX, and at least at a high level, what it is, kind of what it does. It also assumes that you're somewhat familiar with networking terminology. And I also assume that you're somewhat familiar with the concept of microsegmentation. I don't talk about microsegmentation, but obviously when we start getting to the PAN stuff towards the end of the session, there's some reference back to kind of the capabilities of what PAN is able to deliver in conjunction with the NSX distributed firewall. So basically, this is a click-through whiteboard, and it's really about telling a story, right? Telling a story about NSX and how NSX has allowed us to evolve the capabilities of the traditional network fabric in the data center, right? And we also expand that capability out to see how network allows us to very rapidly and easily scale a virtualized network environment and even a virtual environment rather rapidly without having to rely on the physical constraints of the underlying network fabric. And then we also look at what NSX looks like when we scale beyond a single vCenter and a single NSX manager into another site, or perhaps even into the same site, and what all of that looks like, right? And then, of course, we kind of tie in a little bit of the security stuff with the PAN integration at the end, and what that looks like both in a single site and a multi-site scenario, because there are some caveats with both of those approaches. So without further ado, we're just going to kind of jump into this feat first. All right, so site A. All right, so typical VMware environment, three hosts, at least three hosts, connect them to a network, right? And again, this is a vastly simplified network architectural diagram. So for those of you that are network gurus on the call, bear with me. This is highly simplified, really leaning towards showing the capabilities that NSX affords us, and not really based upon actual network design with regards to an NSX environment. Okay, so we have our ESXi hosts, all right, and they're generally connected to some kind of layer 2 switch out there, whether that's a top of rack switch or some other switch within the fabric, and that switch itself is generally connected to some layer 3 device somewhere else in the fabric. All right, now in order to make vCenter and NSX, and actually before we even get to NSX, in order to make vCenter and ESXi work correctly together, we need to deploy a number of required networks. All right, best practices says we have to maintain separation of the different types of traffic we have in the environment. Okay, so if we look at those different types of traffic, we have management traffic. All right, so that's the traffic that is used to allow ESXi to communicate to vCenter, allow the host to communicate with one another. HA traffic also flows along that management network. We have vMotion traffic. All right. Again, we have to keep that separate from all other types of traffic. vMotion is obviously latency sensitive type traffic. We have to have separation for our storage traffic. All right. So whether you're running traditional iSCSI or NFS, or you're running the new vSAN, you still need some kind of separate network for that storage traffic. And then, some environments require things like fault tolerance, right? And then, again, that's another piece of traffic we need to separate. So I generally like to think of the separation of these types of traffic as kind of required separation, and number of ways we can do that, right? If you want to go hardcore and old school, you'd lay down a separate physical network for each one of these different types of traffic, and you'd have like 1 million network cards in each of your hosts to facilitate that. More commonly, leveraging VLANs, right? So we'd leverage logical separation using VLANs to keep this type of traffic separate from one another. So these are what I like to think of as required VLANs, right? So these VLANs and the separation of these types of traffic is required for every single vSphere deployment out there, all right? Doesn't matter big or small. These are kind of the core VLAN requirements, if we're leveraging logical separation, that you need to get things working, all right? So we go ahead and we plumb those VLANs into the environment, right? So we configure the layer 2 physical infrastructure. We have to configure layer 3 too. The router has to know how to route and pass traffic between those different layer 2 subnets, right? And then, of course, we have to trunk those VLANs up into each and every ESXi host, right? That's a given, got to be done, right? We don't do that, nothing works. Then there's what I call optional VLANs. And optional VLANs are really kind of based around the fact that we want to separate different types of application traffic with different types of virtual machine traffic. And this varies, right? So this varies from customer to customer, from environment to environment, right? The type of traffic we want to separate. The most basic kind of separation is a single VLAN or a single virtual machine VLAN on which we separate our virtual machine traffic from all of those required VLANs or that management traffic, right? So generally you have one or more VLANs in any given environment, and organizations might choose to separate the traffic based on servers, workstations. They might choose to separate server traffic even more, either by department or by the function of the server. Applications run on a certain VLAN, web servers run on another VLAN, database servers run on another VLAN, or again, even separate the traffic based on security requirements. For example, a DMZ, or if you have some requirements for PCI or HIPAA control, you generally separate that traffic off to its own VLAN, right? So a lot is required just to kind of get things going. So we plumb these VLANs in. And now with the virtual machine VLANs in place and the management VLANs in place, now we can actually deploy virtual machines to the environment. Okay. So how does communication look between VMs at this point, leveraging the traditional network architectural approach, right? So we have 3 virtual machines, obviously generally more. But if we have a look at this virtual machine on the left here, right? If this VM is on the same network, right, and it wants to talk to another virtual machine on the same network, right? Communication is fairly straightforward, right? Communication exits the host, goes down to the layer 2 switch. There's no routing that happens. So that traffic is then sent back up into the destination ESXi host to the destination virtual machine. Pretty straightforward, no rocket science there, all right? But if there's 2 VMs that want to communicate with one another that are on separate networks, what typically happens there, all right, is VM on the left wants to talk to the VM on the right. They're on different networks. While that VM's traffic exits the host across the layer 2 fabric out to the router, gets routed to the destination layer 2 network and back up into the destination virtual machine, right? So we have hairpinning that goes on. The same challenge also takes place if we have 2 virtual machines residing on the same host that are on different networks, all right? That traffic has to exit the host to the layer 3 device on the physical network, back into the originating host to the destination virtual machine. So a lot of excess traffic, a lot of traffic hairpinning, right? And that's not necessarily a bad thing, but the point I'm trying to make with this is that there's a better way to do it, right? The data center has evolved, and I'm sure you've all heard and understand the concept of the software-defined data center, and that's really the foundation for everything NSX is about, right? We're still bound by the physical limitations of the network fabric today. We're bound by what we can do based on what the architectural design of that network fabric is, okay? And the whole idea behind NSX, right, as most of you should be aware, is to kind of break free of those limitations that are kind of keeping us in one place from being able to truly scale our virtual data center and cloud infrastructures. So what does it look like if we want to scale this environment out? Now, again, we're not even talking NSX yet. All right, so we want to build out a completely separate cluster. All right, maybe we want to grow the cluster, maybe we want to add another host, and again, the same principle applies, right? We're adding another host, adding another cluster, again, single vCenter, right? We have to go through that whole process, right? You have to kind of obviously connect your hosts up to the environment, plumb in those management VLANs into those hosts, configure the optional virtual machine VLANs on that layer 2 switch, and again, trunk those VLANs up into the hosts to the various port groups that are going to support virtual machines. And once we've done all of that, now we can start running virtual machines on that cluster, right? So the challenge here is every time we make a change to the networking that the virtual machines connect to, we have to make a change to the physical network fabric, right? And in an environment where your network is fairly static, this is not really a big deal, okay? But in environments where networks are being requested every day, new layer 2 subnets are being requested for traffic separation and so on and so forth, every time we want to present a new layer 2 network to a virtual machine, we have to go and manipulate something on the physical network fabric somewhere, okay? And, it's time consuming for a start. And second, many organizations out there have some kind of change control process in place that it's not really as easy as it sounds to just add a new network or trunk a new VLAN up into your ESXi environment, okay? So this is where NSX comes into play, all right? So with NSX, there's always a one-to-one relationship between vCenter and NSX Manager, all right? You can't have two vCenters to one NSX Manager. You can't have two NSX Managers to one vCenter. It's always very strictly a one-to-one relationship, all right? NSX, as we know, is really quite simply adding security and networking capabilities into the ESXi kernel, all right? So it's very lightweight, adds very minimal overhead to the environment, and allows us to accomplish really a number of things that otherwise we would have to rely on the physical network for, right? So when we deploy NSX, and we're integrating this network virtualization concept into the environment, we need to add one more VLAN to that required list of VLANs, and that is the VLAN that's going to support the VXLAN traffic, okay? So we go ahead and we plumb that VXLAN into the environment, right? At this point, okay, I'm sure some of you have been through the NSX install configure manage, so this will be familiar to you. Some of you might not have been through that. Once the plumbing is in place, we've deployed the NSX bits to the environment, we've connected NSX Manager to vCenter, we can now start configuring the ESXi host. And part of that configuration is to create a VM kernel port that connects to that VXLAN VLAN segment, right? One of that newly required VLAN that we've just deployed, right? And a component within NSX called the VTAP leverages that VM kernel port to encapsulate traffic. All right, so the VTAP stands for VXLAN Tunneling Endpoint, and the whole idea behind that is we encapsulate traffic to permit virtual machines to communicate with one another without us having to go and tell the physical network about the networks that we've built in the virtual space. Right? For those of you that aren't familiar with VXLAN is, very simply put, it's a way for us to encapsulate the traffic, right? So let's look at this concept very briefly here. So virtual machines communicate with one another leveraging TCP. Okay, TCP is a connection-oriented protocol. So that being said, it's somewhat heavy on the requirements on the network, because for every packet that is sent, a response is required from the destination saying that it received that packet. Right? So there's a lot of back and forth going on with TCP, which in an environment where you're trying to make sure that traffic moves as quickly as possible between different entities within the environment, it can generally add quite a bit of overhead to that traffic flow. All right. So we're able to encapsulate this traffic into a UDP frame, all right, which UDP by nature is a connectionless protocol, right? So send it and forget it kind of protocol, right? Which reduces the overhead required on the network to move traffic between objects that are connected to the physical fabric itself, all right? And I'm gonna talk a little bit more about the VXLAN and exactly what it does and how it does it as we move through this presentation. So if what I've said right now has kind of left you scratching your head, keep scratching your head for a couple more minutes. It'll all get clear in just a couple of minutes, right? So we have this VXLAN protocol that allows us to encapsulate this virtual machine traffic, so we can send it down over the physical network fabric between all of the hosts within our NSX cluster. Okay. So the key requirement for VXLAN is, obviously, we need to increase the MTU size, right? And MTU is really the amount of data that can be put on the wire and transmitted from the source to a destination with a single given transmission, all right? So by default, that's about 1,500 bytes. We need to increase that to 1,600 bytes, right? To allow for that additional VXLAN header information on the front of that packet. Now, there's actually a misconception out there that I've seen quite a few people fall prey to, and that is, when we're deploying NSX, so we have to increase the MTU across the entire network, and that is actually not true, right? So you only need to increase the MTU on the VLAN segment that is going to be carrying VXLAN traffic. All right. All of your other network segments can stay 1,500, unless, of course, you want to increase them. But just remember that. I've seen many people kind of say, well, we have to increase, we have to put jumbo frames across the network, and that's going to cause a big problem. Well, actually, no, you don't. Right? You just need to make sure that your VXLAN segments support at minimum 1,600 bytes. You can go all the way up to 9,000 if you choose, but obviously 1,600 is the minimum. With NSX in place, with VXLAN in place, we can now deploy these logical switches, all right? And another term for logical switch, NSX is the fancy term for, I should say, logical switch is the NSX fancy term for virtual network, all right? Really a layer 2 network, and we create it, and it exists completely in the virtual space of the environment, all right? And we can add whatever layer 2 network segment we want in that space. We can add whatever IP range we want in that space. The great thing about this is I can take my virtual machines and I can connect them to this logical network, or this virtual network, right? And they will be able to communicate with one another, even though this logical network is really not connected to anything down here on the physical network. The physical network has no knowledge that this logical network up here even exists. The physical network has no knowledge of this IP range that I'm using up here. And the physical network at the core could be using a 172 IP address range, or it could be using IPv6, for example. But yet we can use a completely separate IP range, and these VMs can communicate with one another. And this is really where we kind of tie back the whole VXLAN thing, right? So VXLAN is used for virtual machine to virtual machine traffic encapsulation, all right? So virtual machine, I lost my cursor, there we go. Virtual machine number 1 wants to talk to virtual machine number 2 on this virtual LAN segment here, but the traffic somehow has to pass through the layer 2 switch to get to the destination host, right? So what happens is virtual machine sends a packet to this virtual machine, and again, I'm somewhat simplifying this, okay, this is not VCP type discussion, but virtual machine sends a packet to the destination virtual machine. The VTAP, okay, will encapsulate that virtual machine traffic into a VXLAN frame. That VXLAN frame leverages an IP address from the physical network fabric. So now all of a sudden that IP packet that was not routable over the physical network, because it's encapsulated, is now routable over the physical fabric. And that packet is then routed to the destination ESXi host, where that VXLAN header, if you want to call it that, is stripped off, and then the VM to VM traffic frame is passed to the destination virtual machine. Right. So in a nutshell, right, it's kind of what VXLAN does. It allows us to tunnel traffic over a physical network, essentially allowing VMs to communicate with one another, regardless of the network that they're connected to, whether the physical fabric is aware of that network or not. Okay. So now, of course, if we throw distributed logical router into the mix, now we're able to make routing decisions in kernel. Right. So earlier on I gave an example where if virtual machine 1 wanted to talk to virtual machine 3 and they're in different subnets, that routing would have to be hairpinned out to the physical network. Well, distributed logical router is going to allow us to make that routing decision in kernel on the source ESXi host. Right. So virtual machine A wants to talk to virtual machine C, sends the packet down to distributed logical router. Decision is made in kernel within ESXi, and that packet is then forwarded straight to the destination ESXi host on which that virtual machine resides. That routing is no longer taking place on the physical fabric because it's already been done in kernel. Right? So it's kind of it's almost a forwarding of a layer 2 packet at this point once we leverage the distributed logical router. Okay. Any questions at this point before I move on? Fairly commonplace. I think everyone should be fairly familiar with this concept already, right? So, looking at NSX, all right, how do we scale NSX to a second cluster? Okay, so, well, first of all, before we jump to that, with distributed logical router in place, all right, we have our logical networks in place. We have NSX, we have VXLAN. We now have really negated the need for all of these other optional VLANs that have been a requirement in the past. Okay, so we can significantly simplify the environment and remove all of these VLANs from the underlying physical fabric, because now we can relatively easily create as many logical or virtual networks in a virtual space as we need and facilitate communications between VMs without having to touch that physical fabric anymore. Right. So if we extend the same capabilities to the second ESXi cluster, all right, again, I'm just going to let this build out. Okay, so we've plumbed all of the required VLANs into the environment. We don't need to plumb the optional VLANs in. We have distributed logical router in place, NSX, VTEPs, VXLAN, everything is good.
Thanks for taking time to join me today. As always, I hope you found value in these sessions. We've got a lot of great content this quarter. Be sure to subscribe for more updates and videos, and follow me on Twitter for news and updates as they happen. We also have a lot going on inside of services here at VMware. Be sure to look into some of our great new services that are available. Things like the NSX Design and Deploy service, now available from VMware. And if you're a VMware partner, you need to look into our Partner Preferred Services program, where you too can deliver VMware services and learn from our services consultants and professionals inside of our professional services division, so that you can deliver and bring true value and the ultimate in VMware expertise directly to your customers as well. For all this information and more, be sure to follow me on Twitter, and feel free to reach out, and we'll also be able to get you the information you need. Thanks again. I hope you have a fantastic day, and I look forward to talking to you again really soon.